Hi everyone, this is Sandeep Sharma as Electronics.
And today in this video, we will be talking about clock domain processing implemented using System Verilog.
First, we will have a quick recap of what we learned about CDC in my previous video. Then, we will look at what is System Verilog and its usefulness, then its comparison to Verilog. Then we will see how I have coded CDC system using System Verilog, and we will go for simulation of the same. System Verilog is the industry's first hardware description and verification language called HDVL because it combines the features of hardware description languages such as Verilog and VHDL with features from specialized hardware verification languages together with the features of C and C++. The feature set of System Verilog can be divided into two distinct roles. The first one is System Verilog for RTL design, which is an extension of Verilog 2005, and all the features of that language are available in System Verilog. In a way, we can say that Verilog is a subset of System Verilog. Secondly, System Verilog for verification uses extensive object-oriented programming techniques and is more closely related to Java than Verilog. These constructs are generally not synthesizable and are used in test benches. So let's study about the CDC that we will be coding. We will be using synchronous FIFOs for our code. Although we learned about asynchronous ones in my previous video, it's not that difficult. Synchronous just takes two clocks from different sides, that is write and read, and works accordingly. So synchronous FIFOs are the ideal choice for high performance systems due to high operating speed. Synchronous FIFOs also offer many other advantages that improve system performance and reduces the complexity of circuits. Synchronous FIFOs are easier to use at high speeds because they use free running clocks to time internal operations, whereas asynchronous FIFOs require read and write pulses to be generated without an external clock reference. In this diagram, we can see the CDC system comprising of a dual port RAM, which is the memory part of our system, a write control, read control, which are the FSMs for their respective sites, a write pointer, read pointer, which are essentially gray counters. Then we have a combinational part, which is flag logic, that is used to generate important flags such as full, almost full, empty, and almost empty. We also have a reset logic, which is used to reset the flops of the circuit.
The memory array is built from dual port memory cells. These cells allow simultaneous access between the write port and the read port. This simultaneous access gives the FIFO its inherent synchronization property. There are no timing or phase restrictions between the accesses of the two ports. This means that while one port writes to the memory at one rate, the other port can read at another rate, totally independent of one another, which makes the CDC system very fast. The flag logic compares the value in each of the two address pointers. If the difference between the two pointers is 0, the FIFO is empty and the empty flag is asserted. If the difference between the two values is equal to the depth of the part, the FIFO is full and the full flag is asserted. Other flags such as almost empty and almost full flag are generated by the same means. Some links have been given in the description if you want to study CDC further. We will be using System Verilog for coding our CDC system. It is a combination of both hardware description language and hardware verification language, as compared to Verilog, which is just HDL. This slide shows some of the differences between Verilog and System Verilog. Please have a look at them before proceeding further. I have also given some links in the description if you want to study about System Verilog in detail. So let's move on to CDC system implementation in System Verilog. I have used Xilinx Vivado for coding the electronic system. You can use any software. This slide shows the schematic of my system. I have marked different parts with respect to the diagram that I have shown earlier. We will study how I have coded each of them in detail in the subsequent slides. This is a complete block diagram of my system. This diagram comprises of all the blocks, nets, signals with their directions, and the gates, along with the two clock domains. Clock domain 1 is the writing domain and clock domain 2 is the reading domain. The blocks belonging to clock domain 1 are write pointer and write FSM along with the two AND gates. Similarly, the blocks belonging to clock domain 2 are read pointer and read FSM along with the two gates. Those two AND gates are required to generate the clock signals which go to different blocks. Now the blocks FIFO memory, address difference and the flags block. These does not belong to any one clock domain since they handle the signals coming and going from both the clock domains. The whole system starts working when the reset signal first goes low and then goes high. When reset goes low, it resets all the flops of the circuit to their appropriate value. For instance, in write pointer block, the ADDR and ADDR bin signals are set to 0 each. Similarly for write FSM, difference Similarly for write FSM, write enable is set to 0. The read pointers outputs that are ADDR and ADDR bin are also set to 0 and read enable in read FSM is also 0. All the flags are set appropriately depending upon the difference signal. The difference signal comes out of address difference, which is 0 because both write address pin and read address pin are 0. The clocks in the system are write clock, read clock, FSM clock in write domain, and FSM clock in read domain. The FSM clock in write domain is generated by taking an AND of write clock coming from outside of this system and user write enable. Similarly, the FSM clock in read domain is generated by taking an AND of read clock coming from outside of this system and the user read enable signal. The write clock is generated by taking an AND of FSM clock in write domain and the write enable signal coming from write FSM. Similarly, the read clock going to FIFO memory is generated by taking an AND of FSM clock in read domain and the read enable signal coming from read FSM. When reset goes low, the write data is initialized with the value that we intend to store into FIFO memory and then transfer to the read clock domain. This write data value is stored into FIFO memory until the first positive read clock edge occurs after the reset signal has gone high, after which it is transferred to the clock domain 2 and is read by the user or by the other system. Then, at each positive edge of the write clock, after the reset signal has gone high, a write data value is read and is stored into FIFO memory until the read clock positive edge occurs and transfers that value to the read clock domain. At each positive edge of the write clock, address pointer points to the next address where the value has to be written. For example, at the first edge, address pointer points to the 0th address. After the first stage, it will point to first non-zero address. Then similarly, it will increment by 1 at every write clock positive edge. Similarly, at every read clock positive edge, the read pointer increments its value by 1. Initially, it points to 0. Then at read clock positive edge, it will point to first non-zero read address. Then it will increment by 1 at every positive edge of the read clock. The ADDR signal coming out of read and write pointer blocks are gray code pointers, whereas the ADDR bin pointers in those blocks are in binary, which are going to the address difference block, which takes the difference and generates a diff signal. This diff signal goes to the write FSM and the read FSM block, which is used to generate write enable and read enable signals at every positive edge of the FSM clock in write domain and the FSM clock in read domain, respectively. These enable signals tell the write pointer and the read pointer whether to increment the address value by 1 or not. They are also used to generate the write and read clock in their respective domains by taking an AND with the FSM clocks. The ADDR bin signal in the pointer block is made of n plus 1 number of bits, where n is the number of bits in ADDR signal. The extra 1 bit is used to tell the relative positions of read and write pointers, which are used to generate an appropriate diff signal. For example, if the addresses in FIFO memory are 4-bit each, then ADDR signal will be of 4 bits and ADDR bin signal will be of 5 bits. This fifth bit will become 1 when address pointer has made a round and covered all the addresses once. The write address pointer will increment on every positive edge of the write clock. It will cover all the addresses. Then it will increment the fifth bit by 1, which will be indicating that it has covered one round. Now it will stop when it has caught up to the read pointer. That is, the difference between write address pin and the read address pin is 16. In FIFO memory, both the pointers will be pointing to the same address location. At this point, the full flag will go 1. The almost full flag goes 1 when the write address pointer is just one address behind the read address pointer. The write address pointer will not move until the read address pointer has caught up to the write address pointer. When the read address pointer catches up to the write address pointer, empty flag will go high and the system will start working again in its usual state. The almost empty flag goes to 1 when the read address pointer is just one address behind the write address pointer. The state of the write address pointer is decided by the write enable signal coming from write FSM, which takes diff as its input. Depending upon this diff signal, write enable will be 0 or 1. 0 means that write address pointer will stop and 1 means it will move. Similarly, for the read pointer, the state is determined by the read enable signal coming from read FSM, which takes diff as its input. 0 means the read pointer will stop and 1 means the read pointer will start. This slide shows the schematic of dual port RAM, which is the FIFO memory in our system. As input, it consists of read clock, read address of 4 bits, reset signal, write clock, write data of 4 bits, and write address pointer of 4 bits. On the output side, it has read data of 4 bits. Depending upon the System Verilog coding, this diagram shows the inside of FIFO memory block. The first layer of blocks take write address as the input and generate chip enable signal for the corresponding address. For example, if write address pointer points to 0th address, then this block will generate the chip enable signal and enable all the flops residing at that address. These flops will then take write data as the input and store it. As for the read side, when the positive edge of the read clock occurs, depending upon the read address pointer, the mux will take the data from the appropriate flops and transfer it to the output flop, which will then give out the read data. The reset signal goes to all the flops, including the write data flops and the read data flop, and resets them when the signal goes low. This slide shows the flag logic, which consists of two blocks, address difference block and the flags block. Address difference block takes read address in binary and write address in binary as its input and generates the diff signal, which is the difference between the two. The diff signal is taken as input by the flags block and it generates all the flags necessary for the user to check the state of the system. Here are the inside diagrams of address difference block and the flags block. The combination logic for empty, almost full, full and almost empty block can be clearly seen, and the diff signal is generated from write address in binary and read address in binary through the full subtractor logic. Here are the block diagrams for read and write pointer blocks, which are actually gray counters with an extra output of ADDR bin. When the reset signal goes low, it resets the flip-flops and initializes the output to 0. The ADDR output is taken in as the input by the gray to binary converter, which is then incremented by the incrementer by 1 and is converted to gray code by the binary to gray converter. This gray code goes through a combination logic which then decides the next value of the ADDR output. Similarly, the binary code after the incrementer increments it goes through a combination logic and decides the next value of the ADDR bin output. If you have noticed that the ADDR, which is a gray code sequence, is only 4 bit, whereas the ADDR bin is 5 bits. We are using 5 bits for gray to binary conversion, 5 bits for incrementing operation, and 5 bits for binary to gray conversion. Therefore, we need to use a special type of gray code sequence instead of the usual one. Since in the usual one, after the value 01000, last 4 LSPs go in reverse. We do not want that. We want the pointer to go to the 0th address again. That is, after the value, we want the pointer, that is after the value 01000, we want the pointer to go to 10000. Therefore, the combination logic shown in the diagram does that. This shows the usual gray sequence for a 3-bit FIFO memory. This is the reflected code where the bits in any column except the MSB are symmetrical about the sequence midpoint. This means that the second half of the 4-bit gray code is a mirror image of the first half with the MSB inverted. Now to convert this 4-bit to a 3-bit gray code, we do not want the LSBs of the second half of the 4-bit sequence to be a mirror image of the LSBs of the first half. Instead, we want the LSBs of the second half to repeat the 4-bit LSB sequence of the first half. It is obvious that inverting the second MSB of the second half of the 4-bit gray code will produce the desired 3-bit gray code sequence in the 3 LSBs of the 4-bit sequence. The only other problem is that the 3-bit gray code with the extra MSBs is no longer a true gray code. This is how we generate an appropriate sequence for our system to work. This slide shows the read control block, the read FSM. It takes diff, signal, FSM clock in the read domain and reset as its inputs and generates the read enable signal, depending upon the combination logic as shown in the diagram. This slide shows the write control block, the write FSM. It takes the diff signal, FSM clock in the write domain and reset as its input and generates the write enable signal depending upon slightly different combination logic as shown in the diagram. There is a difference between the combination logics of read and write FSM since in the read side we do not have to stop the read pointer. Because the frequency of read clock is slower than the write clock, it will never happen that it overtakes the write pointer. Test bench for simulation consists of the blocks as shown in the image. DUT is our CDC block which interacts with the test part of the test bench through interface. Test is the wrapper of all the other blocks that are shown in the diagram. Generator generates test vectors which are given to driver scoreboard and driver blocks. Environment consists of all the blocks within test which are driver scoreboard, driver, monitor and monitor scoreboard. Driver, after taking in vectors from generator, gives it to interface which feeds the test vectors to DUT. DUT processes the test vectors and returns an output to interface, which interface delivers to monitor. As the name suggests, monitor monitors the outputs and gives it to monitor scoreboard. Both the scoreboards generate a file, one for driver and another one for monitor, which can be used for debugging purposes and also for comparing the data received from the generator and received from the DUT as the output. The code for the CDC system and the test bench can be downloaded from the link in the description. After coding and verifying the code, we can finally simulate the design and get the desired response as shown. User write enable and user read enable along with write clocks and read clock are always on from the beginning. FSM clocks, which are an AND of write clock and user write enable and read clock user read enable respectively, are also always on from the beginning. Reset signal is reset by the user, which triggers rest of the signals in the CDC system. Read enable and write enable are not defined in the beginning, but once reset is triggered, they will be set by themselves. Write data is the input, write address in binary, write address in gray, along with the signals up to diff will be set once reset is triggered. Also, full, almost full, empty, and almost empty flags are set in sync with the reset signal. This slide shows waveforms for write data, write address, mem buffer, read data, read address, and diff signal, along with all the flags. Write data values are C1, 9, A, B3, 1, 2, A0, B8, and so on. The work the CDC system does is that it transfers this value to the read domain. We can verify that in the read domain read data waveform, which we will be doing in the subsequent slides. The values that write data writes are C1, 9A, B, 3 and all the way up to 3, after which it stops writing. Now, if you want to verify, we can look at the read data waveform. The values in it are 0, to which it was initialized after reset was triggered. After that, the values are recorded, which are C1, 9A, B312A0, B8424, and so on. This is the same sequence that was given by the write data buffer as input. Hence, our CDC system works perfectly as expected. If you want to test the code, you can download the codes for CDC and the test bench from the link given in the description. I hope you understood the working of CDC and also you got some insights into System Verilog. Thank you all. Please like, subscribe, and press the bell icon. And also don't forget to give your comments. Did you like the video? And what else should I make in the comment section? Thank you guys.